Hi, it's Jose. Um, Tonight we will be taking a look at an implementation of the Conway's game of life in Algol 68. As it happened with the snake game that we saw the other day, this Live 68 has become one of the demos distributed with the libterm 68 library. So, what is Conway's game of life? So, I expect that most of you will know already what this is about. It is basically a cellular automata which consists in an initial population of cells in a universe. This universe is a grid, it's a bidimensional grid, and you start with a population of cells in this grid, which could be any that you actually start with, you want to start with, and then you start like running. You can call them generations or iterations or turns, but well, you start like running different generations, and at each generation, things happen to the cells in the grid, in the universe. The cells, they influence each other in the sense that the survival or demise of a single cell, of some given cell, depends on the contours of that cell. So for example, as we shall see later, a cell can die due to overpopulation if it turns out that it is surrounded by too many other cells. But a cell can also die of loneliness if it happens that it is surrounded by not so many cells. And finally, a space that was lifeless in the previous generation, in the previous turn, may become habitated by a cell, by a new cell that gets born, also as the effect of surrounding other cells. So, as we shall see, the different rules are very simple. The game itself is quite simple in that sense, and it doesn't take a lot of logic to actually implement it. That said, of course, there is a whole mathematical apparatus around this game and around the, like those simple rules and everything. And well, Conway described that in an article in the Scientific American. I think the number, what is it? 223, back in October 1970. Anyhow, so why the game of life in Algol 68? Well, it turns out, and this is something I did not know until like a few days ago, that the first implementation of Conway's game was actually written in Algol 68 by none other than Stephen Bourne of Bourne Shield fame and Make JT Guy, who I did not know, but now I know. So this initial implementation was written in Algol 68. I suppose that it was written to be compiled by the Algol 68C compiler. I think it was in Cambridge, because that was the compiler written by Stephen Bourne. And I think, from what I have seen around, I think that this initial implementation ran in a PDP machine. I don't know exactly what version of PDP. I don't know if it was PDP 8 or PDP 11 or whatever. In any case, in the rosettacode.org website, and you have the URL there in the screen so you can go and see, there is an implementation of the game of life in Algol 68. Now, I don't know if this implementation is actually the original implementation from Guy and Bourne, but it seems to me that it could be. I have searched, I tried to do a little bit of research, but I could not find any answer on that sense. But it could be, because I don't know of the way that it is written. So, what I did was to take this existing implementation, which is again in rosettacode.org, which is 5.a68, it's this one, and let me go to the end of the buffer. We are talking about 130 lines of code, so it's not a big program. As you can see, it is written using classic upper stropping, so it is a pretty much classic looking Algol 68 code. The upper stropping, it uses uppercase in order to encode the bold words, which in Algol 68 are used for mode indicants like universe. Here you see it's all uppercase, and some keywords of the language like mode here is in uppercase, or struct there is in uppercase, or off here is in uppercase. And to distinguish the bold words from the normal tags or non-bold, which are composed of normal letters and digits, like UPB here, class universe here, and so on. So this is very classical looking Algol 68. So what have I done? So basically I got this implementation, which you can run verbatim, like untouched. It runs in the Algol 68 Genie interpreter. Let's take a look. So Algol 68 Genie interpreter, live.a68, and here you get it. This is like starting from a particular initial configuration. This is like executing a number of iterations or generations or turns. I think it's 570 something of them. I forgot how many exactly. And it paints in the screen. So this is the original program, which is in Rosetta code. All right. So what I did was to take this code, I simplified it, I reformatted it to use the modern supper stropping that we support in GCC and that we prefer to the classic looking upper stropping. GCC also supports upper stropping, but we prefer to use the more modern one. And then I also changed the program to use the libterm68 facilities to get a better user interface. And finally, I added a couple of more of additional features to the program, as we shall see. So the result is, let me see, libterm68. It is in the libterm68 source tree. If you go to demos, you will find it here as live68. All right, so this is it. So as you can see, this version uses supper stropping, and let's take a look at the program. Of course, this is supposed to be a short video. Let's see if I can manage this time. And I can't go in depth, and I cannot go that deeply, like explaining every different Algol 68 feature, language feature in the program. So I will just show a little bit, and of course you are free to study the program by yourself and have fun. So we start with a section here. This is a comment. Okay, well, first, this is a program. So this is an Algol program. This compilation unit is live68.a68. This is a packet. In Algol 68, compilation units are called packets. And in this case, this packet is a particular program. So this particular program is an access clause followed by a close clause, which is a begin end. And in this case, we are accessing the term68 library. So this particular program, roughly speaking, corresponds to the main function, for example, in a C program. So you can actually compile this file and link it into an executable. So the first section in the file in the program is this universe management. Another thing I did with the original program was to add some commentary to it. So basically, what is the universe? So the universe is this grid in which the cells live, and it's called universe in the Conway's game of life. But it is basically a matrix, and each entry in the matrix can be lifeless, meaning there is no cell living there, or it can be populated, meaning that there is one cell living there. And in each entry in the matrix, in each place in the universe there can be only one cell. So you cannot have more than one cell occupying the same position in the grid. So the first thing that the program does is that it declares a mode called universe. You can see this uses this modern stroping. So the requirement for the name of the mode is to start with an uppercase. If we will change it to a lowercase, then this will not be a valid volt word and will not be a valid mode indicant. We'll go back to universe here, and this mode declaration is saying that universe is a row of booleans. So it is a row of booleans. So this row part, it means that it is a matrix. The dimension is 2, or the number of ranks of values of mode universe are 2 dimensionals or 2 ranks. So it is a matrix and of boolean values. Now you can see that in this declarer, so this is the right hand side of a mode declaration, the left hand side is the mode indicant, and the right hand side is a declarer, a mode declarer. So in the declarer we have bounds which determine which is the size of each rank in the multiple, in the row mode. In this case the rank is 2 again because it is a matrix, and we see that it is a square matrix. It's a square. The universe in this program is a square. And so how many rows you have and how many columns you have. You have udim for universe dimension rows, and that same udim rows and columns. And we are declaring this udim here right after the mode to be 45. Now, this is an identity declaration in which you are ascribing the value 45 to the identifier udim. Okay, and as you can see, here is one of the examples in which you see in Algol 68 that an identifier is actually used before it is declared, which is perfectly valid. Of course, the requirement is that at this point, when you are actually referring to identifier in this mode declaration, in the same range where this mode declaration is, udim should be declared, and that is the case, is right after. And udim is an identity declaration that ascribes the number 45 to udim. In Algol 68, this is the way of declaring constants, what you will call constants in other programming languages, and in Algol too, constants. Once the value 45 gets ascribed to the identifier udim, in the range where this identifier, in the range where this value actually, this identifier is visible, you cannot change the value that is ascribed to that identifier. So udim is going to be 45 in this whole range of the program, in the whole program. So it is a constant, basically. You cannot change its value. All right, so the universe in our game of life is 45 per 45. 45 rows per 45 columns. It's not a big universe, but it's our universe. And then we are still in universe management, and we have a few routines that actually operate on the universe. So the first one is called init, which it initialized a universe. So you pass to the routine, the procedure init, you pass a universe, and it initializes it for you. So initially, the universe is lifeless. There is no life in the universe, and this is what this routine does. Interesting thing. We are not passing as the only argument to this procedure. We are not passing a value of mode universe, because if we did that, if we will do this, then we will not be able to actually modify the different booleans in this universe, because we will be passing a universe, but in Algol 68 the only way to mutate memory is through a name or a reference, and in this case we will be passing the value itself, and you cannot assign to a value itself because it would be like assigning to 10 or to 5. It is the same. It doesn't matter if it's like a basic fundamental value like 10, the integral 10, or in this case a matrix of booleans, a multiple of booleans. It doesn't matter. So instead, what we do is that we pass a name to a universe. In Algol 68, name is the way of referring to, you could say, references, but they are called names. So we pass the name of a universe, U, and then we iterate in the different rows of the universe, and then each rows we are gonna pass a reference, a name to that particular row as a multiple of booleans, as an array, one-dimensional array of booleans, to another routine which is called init row that we will see, I guess, later. I don't know where it is defined, probably down there somewhere. And note that this is trimming, like this is okay. We get U, which is a name of a universe, a reference to a universe, and then we select the corresponding row. And then in the second dimension, which is the column, we don't specify anything. And what this does is that this is creating a new descriptor for the dope array, which is this matrix. But this descriptor is basically, it only has one dimension, because for every index that you specify in the trimming, there is one less dimension. If you specify the row, you get the columns, right? And so basically what this achieves is that we are passing a reference to each row of the matrix, one after the other, as the loop gets elaborated. Yes, when you index, when you slice or you trim in Algol jargon, so when you index, you access to the elements in a multiple value, in an array, you get values of whatever mode. But if you index or slice or trim a name, because remember that you are reference to a multiple, then what you get is a name to whatever element you are referring to, or in this case you get a name or a reference to the row. So this may sound a little bit confusing, but trust me, once you interiorize the different orthogonal concepts, everything is very natural and very easy to understand. All right, so long story short, in it gets a reference to a universe, a name of a universe, and it initializes it all to false. There is no life. Then we have another little routine here, which basically it gets a universe, and it prints a representation of this universe on the screen, and basically it iterates through all the rows and all the columns in the matrix in the universe. It checks if each entry actually is lifeless or it has life in it, there is a cell in it, and then in case there is a cell in it, oh, okay, I see there is a bug here. Yeah, I changed this. Anyway, so it uses the term goto and term put routines from the libterm68 library that if you saw the previous video on the snake action game, basically here is okay, in this viewport of the terminal, go to this particular coordinate and then write something into it. Now I am realizing that that I don't need to have this conditional expression here, this conditional clause here, because actually it's already been checked that the cell has life in it. So right, so this is better. So basically, and then puts what? This black circle is one of the Unicode drawing characters that are provided as well as nice constants by the library. So this given, again, this given a universe, it actually prints it on the screen in the viewport. Then the next routine here is called insert glider. What is a glider? So probably you have seen this symbol out there in the internet because at some point it became like the symbols of hacking, like hacking in the good sense of the word. Well, this is a glider. What is a glider? A glider is this configuration of 5 cells that once you have it, if you simulate the game of life starting with a glider, the glider basically moves or glides like rotating. It's very funny to see. We will see it later. We will do it step by step. So it basically moves, and it always moves in the sense that it is a cyclic pattern. At some point, it goes back to this original configuration, and it's very funny to see those gliders because they are like rotating. They are like rotifex. Like, I don't know if you know a little bit about protozoa through microscope. They are like little rotifex, like moving around. Anyway, so this routine, what it does is that you pass a universe or a reference to a universe, and you specify a coordinate in row column, and then it's like, okay, insert a glider there. Now it happens that the coordinate that you are passing is the one where the cursor is right now in the comment. So it is the center of the 833 little window there. So that's why, well, so this one is row minus 2 col plus 1. Row minus 2 col plus 1 true. It is this one. Row minus 1. No. The coordinate is this one. What is the coordinate? Oh, the coordinate is this one. This one. Okay, well, whatever. So you specify this coordinate. So 2 less, 1 plus. So this is the first. 1 less, 2 columns. This is the other one. And then those 3 is this. So in this case, we are slicing the multiple, and it's obvious how. But in the last case, we are using a trimmer, and so this row basically is the row that we are, and this col plus 2, this is actually trimming. So the result of this, so this trimming here, it yields this row, a reference to this row, and then it is assigning a multiple of 3 true values to it in one step. This is called a row display, and it is in a strong syntactic context expecting a multiple of booleans. So basically this inserts a glider in the given coordinate, which is here and not there. Now, one thing, you may be wondering, what if I pass, for example, the coordinate 1, 1 into the universe? Then this one, it will be row minus 2, it will be coordinate minus 1, and you will be out of the universe if the universe starts at bounds 1, 1. And yes, it's true, it will happen, but what will happen then? There is no checks here. In other programming languages, you will need to put an if here and say, well, if the coordinate is out of, well, you will have to actually handle a lot of special cases and emit errors consequently. Now in Algol 68, by default you get runtime checks in accessing of multiples. So if there is a bug in the program and basically it turns out that you insert a glider and it results that not the full glider can be in the universe, you will get a runtime error pointing to you to the particular line in the code where well, the invalid access to the multiple was made. Okay, then we have the routine next, which is actually where the meatiest stuff is. This is what implements the algorithm, even though it's not that big, but we will skip it for now. And oh, here is the init row that it gets. This time is not an array, a matrix of booleans. This time it is a reference to a row of booleans or a multiple of booleans. And then it's basically from its lower bound to its upper bound, it's setting it to false. Now, every time that you get a multiple passed to a routine, you have to check the bounds, and in particular, you cannot assume that the bounds of the multiple that you get start as one, start for example at one. So you cannot omit the from lower bound row. You have to specify it because the bounds could be any sort of bounds. There are tricks around that, but this is like the canonical way of doing it. And then it is just setting it to false. And then again, what you are getting here is the name of a multiple of booleans, not a multiple of booleans. So that's the reason why you can assign to it. So by row here is a secondary row here, it yields and the name a reference to an array to a multiple of booleans. Then you index that, and the result is a name. Is a name to that particular element, the reference to that particular element, and then at the left-hand side of an assignation, of an assignment, you have a ref of bool, and on the right side you have a bool, and actually that's how it works. Okay, then we have here another routine called insert Gosper gun. So what is a Gosper gun? So a Gosper gun is one of pattern that someone called Gosper found, that it has two characteristics, as we shall see when we see it in action. One is that this pattern basically is cyclic. So as we can see, we will see those different things will be moving and interacting with each other, but at some point we'll go back to the initial configuration. So you can have them running forever, basically. And as a very nice side effect, this pattern, it actually shoots gliders, and that's why it's called a gun, I suppose. That's why it's called a Gosper gun. So this routine, basically, it inserts in a universe, it inserts, one Gosper gun, this configuration. So observe how we have an identity declaration here for a multiple of chars, a matrix of chars of 2 dimensions, and then we have a row display here, and we specify the contents like this, which is very visual. And basically any character which is not big X is lifeless, and any character which is big X, uppercase X is life, is a cell. So that's how it works. So then it iterates in the template here, and then it sets in the universe that we pass, if it is big X, it is populated, it's alive, otherwise it's lifeless. Now, we did not use universe here, we did not put ref universe here, and the reason why is that we want to emphasize that, okay, first, Algol 68 does structural type equivalence, and it's actually very serious about that. It's not like, well, yeah, but, no, there is no but. Literally, you can always substitute a mode indicant like universe by its structural definition. It's not like other languages where, yeah, but, there is no buts here. Algol 68 is orthogonal. So you can always substitute that. So here, we wanted to emphasize that, well, observe that you don't actually get also a position where to insert the Gosper gun. It always inserts them starting at 1, 1 in the universe that you pass. but as we will see later, you can actually, this doesn't have to be an entire universe. This can be a portion of a universe, a rectangular portion of a universe, and that is something that you also do by trimming. If you are a Fortran programmer or an APL programmer, you will probably be very used to dope arrays, and which it is what Algol assisted multiples are, and this doesn't sound like very extravagant to you. But if you are a C programmer, for example, the world of dope arrays is probably not that well known to you, and this may sound like surprising and very useful, and it is. Well, anyway, yeah. So this is insert Gosper gun. It inserts this Gosper gun, which is an awesome thing. And there is also another routine here, which is similar but different. And this is one of the extensions that we added to this program. So basically, you give a universe or a region in a universe, and then you specify a file name, and it opens the file that is specified, and it reads characters from it, as many as there are in the file, and as many as they fit in the universe that you pass, or the region of the universe that you pass, and then it interprets that big X in the file corresponds to a cell, and any other characters corresponds to lifeless. Now, it is interesting to look a little bit at this particular routine, because it is written in a way that it actually minimizes possible runtime errors. So what I mean with this, okay, so first it opens the file by using the fopen, which is part of the POSIX prelude, which is available by default in GCC. You pass file name, you say we are reading the file like read only. This is an identity declaration that you are ascribing the resulting file descriptor, which is an integer, into the identifier fd. And then if fd is not -1, then you actually do work. If it is -1, then you print an error message explaining why the file could not be open. You have the p error, which is also standard function, standard routine, argv, which is another one to get the, and POSIX exit, which is exit, like POSIX exit. It exits to the operating system, passing an exit code of 1, which is an error. Alright, so first, you know that in Algol 68, in the if part of a conditional clause, you don't have, like in other programming languages, like a Boolean expression, or you have an inquire clause. And the inquire clause, it should by itself, it should yield a Boolean value, but it can contain declarations, it can contain all sorts of things. And in this case, it has this declaration first, and then it checks on the value of fd. But the declaration, the identifier, the range of fd, it actually covers the entire clause. So you can refer it in the then part, but can also in the else part, which is quite a nice thing to do. Anyhow, so if we actually manage to open the file, then we iterate from one row, we set it from 1 to udim, and then inside, so for as many dimensions you deem that the universe has, and then while we can continue reading actually lines from the file. So the get s is a standard routine in the POSIX prelude that if you specify 0, it reads until a string from the file until the end of the line, including the new line character, or until there is an end of file condition. And if there is an end of file condition, you get the empty string. So basically, this is one for clause, or one loop clause that is for row from 0, which is implicit to udim, to the dimension of the universe, while there are still, I can still read lines from the file, Then I do the column. So basically, those the rows, and then we do the column, which is for call from 1 to the number of characters I have read from the are in the line, but make sure to not get out of the universe. And then basically it does like the previous routine, it compares with uppercase X. So as you can see in this loop here, in this loop and the nested loop here, it does processes rows and columns in a way that you don't get out of the universe and you actually only process whatever is in the file. I know, I suck explaining these sort of things, but well, you have the code there, you can read it by yourself. One thing though, note that this POSIX exit here is actually exiting the program. And if you go to the else here, you print the error message, then you exit, then obviously this doesn't get executed. However, why there is a skip here? Well, Algol 68 is an expression-oriented language, and every for example, this conditional clause is an expression, and in this case, this expression is in the body of this procedure. Is this enclosed clause, which is itself is the body of this procedure. And by the way, let's do. We don't need the closed clause because the conditional clause is enough. So this conditional clause is in a strong context, syntactic context, where void is expected, because this particular routine, in this routine text, is yielding a value of mode void. And I think that the skip here could be it's actually not necessary, but if this was a procedure that will return like an int, for example, then if you do something like this, you still need to specify a value of whatever mode expected there, otherwise it's a syntactic error. And when you don't care what value you put there, like in this example, you don't care because you are exiting the process, you use a skip, which is the best thing since sliced bread. Is one of the things in Algol 60 that I like most. Anyway, I don't think you need a skip here. You don't need it because the POSIX exit itself, it yields void, and if it would yield any other mode, a value like an integer, for example, it will be voided because this is in a strong syntactic position where void is expected, because the coercion, it jumps into the else part. Okay, this is sort of advanced Algol 68 stuff, but again, I don't want to discourage anyone. It's the other way around. I mean, it may look like complicated, but trust me, it's not. Once you know the different concepts, you can combine them orthogonally. It's not complicated. It looks like it, but it's not. It requires some patience and some work though. Anyway, and then there is another, so this basically reads a file and interprets the file contents as cells or no cells, and creates a universe, fills a universe with it. Then we have this insert glider squadron, which it does exactly what it is. It does. It inserts a squadron of gliders that we will see how they look like in the given universe. And then we have a few routines here which are related to the interface, the user interface. I'm not going to extend myself here because they are very similar, if not the same, that we used in the Snake action game. So I address you. You can go to watch that video if you are interested. Then here we have a small routine which is that it updates the turn also in the user interface. This is another little routine that we also used in the other demo, which draws a frame in some particular viewport in the terminal. And then here we start the program itself. So basically we make a universe. So here we have universe, Conway's universe. So remember that the mode of universe is this declarer here. So then again, you could always substitute universe here, the indicant universe, with the other definition, with the full definition. It will be always equivalent to it. So what is this? This is a variable declaration. So basically, a space, it gets allocated, in this case on the stack, because this is equivalent to do this. You could have done this, but we didn't. So this allocates in the stack basically a matrix of 45 per 45 booleans, and the resulting name or reference, because the mode of Conway's universe here is a ref to universe, it's a variable, it's not a constant. Then we initialize it, so we fill everything with false values in it, there is no life there. Now, if we have invoked the program with no arguments, argc is 1, like in C, like in POSIX, because argv includes, it counts the name of the program itself, which is useful for diagnostics. Then, but if we have not specified any file on the command line, then it inserts a Gosper gun starting in the first row. So you see, this is what I was talking about before. Here we are trimming the universe, the complete matrix, and in this case we are passing from the fifth row on, and the first column on. The reason that we are putting here a colon and we are not doing this is because we want the bounds of this trimming to start with 1. Again, this is, if you are interested, you can read, I don't know, the formal introduction, whatever. And then we are inserting a squadron of gliders. However, if we have specified an argument in the command line, then we interpret that as a file name, and then we actually, instead of putting a Gosper gun, we load the contents of the file. Otherwise, we complain. Then we create a little user interface with a banner, some commands. Now you will see how this works. This is using the libterm68 library, so it is term open. It initializes an initial viewport, which is the whole thing, and then we have other viewports, which is the one with the turn number or the generation number. Another one, messages with some message and the commands which are available, and then the grid. And it is in the grid where we are gonna print the universe and keep it updated as it changes. Now, the size of the grid is the size of the universe, but on the rows is +2 rows, because it has to take into account the frame, which is this and this, and in the columns is +3 columns, and I have no idea why. But anyway, at this point I forgot about why. But it's slightly bigger than the universe. Then it saves the state of the terminal, it switches the terminal to row mode, it hides the cursor, it says this time and min terminal attributes, so you can press a key and it will not freeze the process waiting for the key. Now, then it clears the terminal completely, and then it shows the banner, it frames like the grid, and then it calls our routine repr and passing the initial universe that it's been populated, initialized from with the Gosper gun and the gliders squadron, or with the contents of the file that we have provided. Then here, so at this point we should be seeing that on the screen. Then here we have, this is a declaration of a function of a routine mslib that uses the FFI support to call the C or the system uslib function, and it gets an unsigned int, so it's a bit and returns a bit, an int. This is microslib basically. Then we have initialize some variables, pause color, then turn we are, how much to wait in each iteration between turns, and as we will see, you can specify as you run the program how fast the simulation happens, and you do that by defining speed step. Then we show the pause commands. You will see what this means. We set the turn to 0, and this is the main loop of the game of the program, which is that it checks if there is key press. If it is Q, it exits. We are done. If it's not Q, then we have two main states in the game. The game can be paused, and then if it's paused, we have the pause command. Sorry, if it's not paused, this is the not standard operator for booleans. So if it's not paused, if we are running, you can pause, or you can increase the speed of the simulation, or you can make it slower. Making it faster, it has a limit. I mean, because otherwise you can actually underflow the speed step, but basically you make the step smaller or bigger. So this is the running mode. Then it sets the new turn, and then it calls this next in the Conway universe. That is the last routine that we will see, which basically, given the current state of the universe, the current universe, it calculates the universe at the next turn. Basically it updates the cells, the ones that die, the ones that get born. But if we are paused, then you can run to reannotate, or you can set the color mode, which is useful if you want to see it have better visibility of which cells are new or not new, or you can step. So you can pause and go simulate step by step. This is all additions that we did over the original code in rosettacode.org. And then you micro sleep, and then you clean up, and you are done. Okay, now at this point, before looking at the next routine, I'm gonna show you this program actually running. So leave 68. So we have not specified any command line option, and so it has loaded the Gosper gun, which is, you have it at the top, and then this squadron of 5 different gliders. So if we run, so we press R, you see how the gliders, they get to the border, and you see how the gun is actually firing more gliders, and but then at some point the effect of what is going on outside of the gun is gonna reach the gun itself. Oh, you see, and the gun itself is gonna get destroyed. And this particular configuration, it ends in these recurrent states, right? So if we pause, you can go step by step, and you see the universe gets into basically a cycle, and no more life is gonna happen. Well, there is actually more life. Look, if we press C, which is color mode, and then we step, you can see that this is the new generation. This is a new generation, so the red ones died, the green ones became alive. Same thing again, same thing again, same thing again, and again, and again, and again, and again, and again. So if we continue, basically, well, it never gets different than this. Okay. So if we run it again, and we set color mode, and then we run, well, you can see what happens more or less with the different cells. It's fun, and it's interesting that this particular configuration, well, it kills the gun. Okay, pause, we can quit. Now, the other mode of the program is by specifying a file, and I think I have a file here. Where is it? Hack sleep term 68 build. Yeah, in unif.txt, as you see, what I have in this file is two different Gosper guns, like facing each other and symmetrical. Look, life 68, unif.txt. So in this case, instead of loading the defaults with the squadron and the gun, it's reading from the file. And this particular configuration, this particular world, you see the two guns, and the two guns are firing those gliders, and then the two gliders are resulting into those two little cubes, and then the next gliders will annihilate mutually. So maybe it's better to see. So you see the gliders, and then at some point they collide, boom. And then in the game of life, when you have a configuration which is like those little cubes of 2 or 4 cells, they are stable, they don't change. Look, they don't die, those cells are eternal and they are static. However, the next pair of gliders fired by the guns, then first they kill those cells at the left, and then look at what happened, pop, and they disappear. So this is a fun configuration because you can run it forever, and you have the two guns like firing to each other, which is fun. Anyway, by the way, you can run faster by pressing F. You can run slower by pressing S, as we can see. We have seen already how that works. You can pause, you can step. Okay, so this is basically the game, our version of the game, like working. Now, the last thing we are gonna see, because again this is getting too long, is this procedure next, which basically is okay. It's not that long because I put a lot of comments here, but it's very interesting, and it's the best part of the code that is in Rosetta code, rosettastone.org. And I don't know again if this is the original code from Born and Guy, but it's a very interesting way of doing this. So basically you have the next, you get a reference to a universe, a name of a universe, which contains some particular state of the universe with the cells. And then, okay, how would you do this? Now, what are the rules? Let's go down here. So the rules of the game of life is that, 1, any life cell with fewer than 2 life neighboring cells dies, as if by loneliness. Any life cell with more than 3 life neighbors dies as well, but in this case it's because of overcrowding, not enough resources. Then any life cell with 2 or 3 life neighbors lives unchanged to the next generation. And any lifeless cell with exactly 3 life neighbors comes to life. New cells get born. So those are the 4 rules of the game of life. So if you start with a universe, then you have to somehow iterate over all the different cells of the universe, the position of the universe, and update them for the next turn. The rules are simple. How will you do that? Well, if you iterate and you have you iterate in a loop, in 2 loops nested, and then you do the right thing. But the way this code works is that using the array features of Algol 68 is that it declares here a variable which is a window, and this window is a matrix of booleans, but with the following characteristics. It has 3 rows, so it always has 3 rows, this window. It's a 3 rows window, and the bounds are from 0 to 2. They are not the default 1, 2, 3. They are from 0 to 2, and you specify it like this. The lower bound is 0, the upper bound is 2, And we will see that the reason why using those bounds, zero base bound, is to make it easier to use with modular arithmetic. And then the columns, the lower column is the lower bound of the universe minus 1. Remember that the universe is from 1 to udin, right? So it is from 0 to whatever number of columns the universe has plus 1. So basically you have the window, it is 3 rows, and it is 2 columns wider than the universe. Why? Because of the horizon. So then you set the horizon here, the initial version of the horizon, and then you move the window down the universe. And I try to depict this in those comments. So initially you have the universe, so this is the universe, 45 or whatever number of it, of cells. And then the window you first created, so this is the first row of the universe, right? Here it will be like the top left corner, and this is the top right corner. So you first put the window in a way that the top row of the window is horizon, which is false, it's death. And the columns, the first column of the window and the last column of the window will always have false, because it's the horizon which is always death. And the second row of the window corresponds to, gets the same values that in the universe, and the third one we don't know at the beginning of after this initialization. And then at each iteration of the loop, basically what we do is that we slide the window down through the universe. And why doing this? What's the point of doing this? Well, because for each entry in the universe, we are gonna first specify, we are gonna count how many live cells this cells has around it. And note that we have to do this in a small three blocks of cells. And if you would be coding this in other programming language, probably you will start with the first one and say, if the number of column is bigger than 1, then look at the column at the left, for example, and count it. If it is bigger than 1, the row, then look at here. So basically we will have if, else, and we will have like a lot of logic different cases here. Because if you start with the 1, 1, you have to check this for life, this for life, this for life, but you don't check this because it doesn't exist, this because it doesn't exist, this, and so on, right? So that will be the classical way of doing it. But with this window that is using the Algol 68 support for actually having trimming, because the data is always the same, it's always names that are, so references, okay, I don't want to get annoying. So basically you have the window. So what the window gives you is that for every for every character in the window, in this row here, either you can always actually check the 8 characters around it without a need for special cases. So this is how it works basically, and you slide the window down. And this is done in this loop. So first, for each row in the universe, you starting with that initial window, then you adjust the window, but getting the next row into the window. And you do that with modular arithmetic here. This is the modulus operator, standard operator. And this is why the bounds start at 0, by the way. And then once you have your window positioned, then you use it to actually check, to calculate, you check in the window for each entry and which one is, how many alive cells they have around, and then if it has changed, So if some particular cell was lifeless before, but now it is inhabited, then you have to actually put it in the terminal. Otherwise, you make it lifeless. And that is how the next routine works. So I'm sorry, I know that the explanation is like shit, but you can of course read the code. So, and we are done. This program is now part, well again it's like less than 350 lines, I think it's quite good. It is essentially the same algorithm that is in the Rosetta code site. It's maybe the original implementation from Born, I don't know. And yeah, if you like the game of life, you can have fun with it. And I myself learned a lot about this game by actually doing this little port of this program. So this is all for today.